Yeah, thanks. So I'm Shunsuke Mamoru of NHK. My presentation is about the browser playback of VVC Multi Layer bitstream. So for those who are, it's very difficult to see. For those who are not familiar with Japanese broadcasting background, so I'd like to introduce something. So NHK is a public broadcaster in Japan. We have also some private broadcaster networks across Japan. And in the current media landscape in Japan, we have a traditional broadcasting service using a terrestrial wave and satellite wave. And also in Japan, global streaming services such as Netflix, Prime Video, and Disney Plus are more and more popular. So according to this trend, Japanese broadcasters are increasingly providing simulcast services using broadcast plus streaming, and also catch-up on-demand services. So NHK Plus here in this logo, so it is our brand for providing streaming service and on-demand service, also catch-up services for using internet. And TVer, which is the similar service provided by the private broadcasters. So actually, although we have started 4K and 8K broadcasting service using satellite with the HEVC codec, but actually traditional terrestrial broadcasting service has started since 2001. So more than 25 years, we use MPEG-2 system. It's surprisingly old. So we think it's time to move to the next generation broadcasting services. So now we think VVC is the most strong candidate for the core codec of the next generation broadcasting services, and which provides approximately 50% bitrate reduction compared to the HEVC, and also which VVC supports HDR, 360-degree video like VR, and also scalability functionality. So actually VVC was already adopted many global broadcast standard like Arrive, ATSC, VDB-VB, and SDTVD. So yeah, okay. But actually, just bitrate reduction or visual quality improvement may not justify the start of the next generation broadcasting service. So we focus on the personalization as a new feature of the broadcasting services. So which is realized by VVC Multi Layer coding. So Multi Layer coding is a technology that can where different type of content like low resolution and different type of resolution. Those videos are combined, are coded together into a single bit stream, and subset of the full bit stream called base layer. If you receive the base layer, you can decode the lower resolution image, and if you get the full bit stream, you can decode the enhancement layer. I mean, high resolution image. So this type of decoding mechanism can realize the personalized service, maybe depending on the decoding devices. And also one another use case is called content scalable. So main content and the main content with some additional information such as the sign language are coded by the multi-layer coding. So at the receiver side, both of them, I mean main content and the main content plus sub-content, can be obtained by decoding those bit stream. So the user can switch this content upon their preference. So this type of service may realize the personalization. So, okay. So for streaming services, web browser are a key platform across PC, a mobile device, and TVs. So as of now, the support of the HEVC in browsers is reportedly more than 93%. But actually for VVC, none of them supports. So browser support is critically important when selecting the codec for the new service deployment. So as I said, VVC is adopted for broadcasting standard, but the lack of the VVC browser support would become a major bottleneck for the unified service delivery. So as I said, currently we use MPEG-2 system for the terrestrial wave and the H.264 for internet service, streaming services. So we need to store both of them. So it's a kind of inefficient. So if you use VVC and the browser and the TV set also support the VVC decoding, so it's much better workflow. So in this work, we show the implementation and evaluation of VVC playback on browser, Chromium browser. So this is the media pipeline in Chromium. So media file is fetched from the network, and the decoder calls the FFmpeg as a backend of the decoding library. So after decoding the media file, those files are output to the window. So we think if we implement VVC decoding capability into the FFmpeg, it makes VVC playback on Chromium possible. So we have some options of VVC decoder. So the left one, okay, okay. So the left one is VTM, which is a reference software used in the development in MPEG and ITUT for VVC development. So it's a kind of readable and implementable in somehow. And also multi-layer coding is supported. But actually, it is purely developed for the standard development. So parallelism is not considered. So it's not practical to integrate to the FFmpeg. The second option is VVDEC, which is open source VVC codec reversed from the HHI, from 44HHI, which is also very nice codec, readable and implementable, and also software optimized. So so it's a very high-speed decoder. It's kind of broken, but it says compared to VTM, you can see, you can see 80 times faster than the VTM. So it is very nice decoder. So the problem is that the VVDEC is lack of the multi-layer decoding capability. The third option is FFmpeg built-in decoder. So it's quite nice, already implemented in FFmpeg. But as of at the time of implementation, our implementation, multi-layer coding is not supported. And actually, we have limited know-how, so we decided to use VVDEC. And we decided to extend VVDEC with a multi-layer decoding capability. So since the VVDEC does not support multi-layer decoding, so some decoding module for multi-layer part is ported from BTM. So after after porting the modular functionality into VVDEC, we tested the decoding performance, and we confirmed that we could successfully add the modular decoding capability while maintaining the decoding performance, mostly the same speed. So at last, as I show the new use case, content layering, so user want to switch between the content layers. So we add a new attribute to the video element to control the selection, layer selection. So after fetching media file, firstly parse the layer information from the bitstream, then pass to the user by introducing new API to notify the layer information parsed from the bitstream. And upon the user request, so you use the FFmpeg, the user request control the FFmpeg decoding process and also rendering process. Yeah, this is a video clip of decoding playback on VVC playback on browser. So as you can see, upon the user request, the video the layer is seamlessly switched between the main content and the main content plus sign language. Yeah, so a summary, my presentation summary is that so we implemented the browser playback of VVC Multi Layer bitstream on Chromium, and the FFmpeg is extended. VVDEC is extended with a Multi Layer decoding capability and integrated into FFmpeg. So that makes the Chromium VVC decoding possible. And seamless switching was also introducing by the new HTML element. Yeah, that's it, my presentation.
Thank you. Questions from the audience?
Hey, very nice demo, thank you. A question about the demo. You are exposing here, and it's about the integration with the HTML element. Are you exposing both the output layer set ID and the layer ID? And why isn't the output layer set not sufficient? I don't see, for example, the difference between the two.
Yeah, actually, yeah, it's a kind of technical detail, but the OLS includes in this case, OLS 1 includes both base layer and enhancement layer. So if this PC is high performance, I mean, it's not that performance, but if this PC can decode multi-layer bitstream, so you can use OLS 1, so you can change the content seamlessly. But if this laptop is not that very nice one, maybe you cannot decode a multi-layer bitstream, so you can choose OLS 0, which is the only base layer. So that's kind of scalability. For that kind of scalability, we expose those both OLS information and all of the OLS information.
Any other?
And well, thanks for the presentation, very good. So by doing this, do you have a native FFmpeg? So compared to the previous presentation, you are not doing any web SM or anything. So how's the performance for typical content, 2K or even 4K? And what is with the overhead of a scalable part?
Actually, I didn't mention about that. Sorry about that. But actually, Fraunhofer HHI reported Watson-based VVDEC integration into the browser. So, and they said, and actually I talked with the developer of that project. He said that Wasm is, I'm not sure, correct me if I'm wrong, but Wasm, the performance between Wasm based and the native decoding is faster. That's why we decided to implement. Yeah, actually, Benjamin.
Yeah, one of the issues there is the different WASM things supported by different browsers, say multi-threading and so on. So some browsers do not support multi-threading. That is a big boost for and this kind of stuff. So having it native in C plugged into a browser is significantly faster. But it's working in WASM as well, up to a certain resolution, bitrate, and so on. But it takes, of course, it's an abstraction layer that takes performance.
And also, I heard something about DRM matters. So, Wasm can handle DRM. Yeah. Oh, okay.
Any other? Okay, thank you so
Thank
much.
you.